chain rule. So what I'd like to do now is work through some examples of using it to solve various problems and describe some things. Document camera. So some example problems type, example problems here in the left. Some or all of these, I think, are from taken from Schaum's outlines of calculus books. The first one is kind of in the spirit of the example we did in the lecture. It's taking that mixture of partial derivatives, the sum of the squares of df dx and df dy, and seeing what that looks like in polar coordinates. Questions 2 and 3 are much more of a kind of applied type problems to the geometry of a cone and a cylinder. So in question 2, you've got a cone of certain dimensions, and its height is increasing and the radius is decreasing at some fixed rate. Well, if the radius decreases, that will tend to shrink the volume, but if the height increases, that will tend to increase the volume. So the question is, what's the combined effect? And how fast is the volume of the cone chaining at that particular moment in time, given those starting values, 15 centimeters and 10 centimeters. Similar types of questions about a cylinder, about the volume and the surface area. Then finally, question 4 is about the motion of a particle in the plane, but this is where the motion is parametrized by a time variable t. So the coordinates x and y are given as functions of the variable t, the time variable. And what question you ask? Being at what rate is the distance of the particle from the origin changing at a certain time, at time t equals 1? Well, the distance of the particle from the origin is the radius r. So it's not surprising that the chain rule equations will come in use there, because you want to find out the derivative dr dt. Okay, but you don't have the radius specified explicitly as a function of t, but you've got x and y specified as functions of t, and the radius is in turn a function of x and y. So it's the chain rule that will get you the thing you need there. If of time, I'll also might introduce the spherical coordinate system, which is a kind of polar coordinate type, thing about radius and angles, which is used in 3 dimensions, and what the chain rule equations or what the Jacobian determinant might look like there. Okay, so let's have a look at question 1. Now, this is going into polar coordinates, so we'll be able to make use of the partial derivatives we obtained from the example in the lecture, okay? Okay, so from the example in the lecture, we'll just record what we found there. So we have dx dr, dx dy, and no, sorry. What's going on? What's going on? Yeah. So we had dr dx, dr dy, and d theta dx, d theta dy. We did these last time, so dr dx was just x over r. Dr dy was the similar thing, y over r. D theta dx was d theta dx was minus y over r squared. And d theta dy was x over r squared. If you wanted to, you could replace all the x's and y's on the right-hand side there by the r cosine theta or r sine theta. But we'll keep. 0 here, 2xy minus 2xy. So this just goes to 0. So that's good. Simplifies it down. And in the other coefficients, well, you see that both terms have the same denominator, so you can just squash those fractions together. And in the numerator, you've got x squared plus y squared, which is r squared. So actually, this coefficient here it's just 1, because it's x squared plus y squared over r squared, but x squared plus y squared is r squared. So it's x squared plus y squared over r squared, df dr all squared, and here it's x squared plus y squared over r to the power 4 df d theta all squared. So that's simply, this is just 1 here, so this is just df dr, all of it squared, but this is 1 over r squared. We've got r squared in the numerator, but r4 in the denominator, so it's 1 over r squared df d theta squared. So that's kind of the finish of the translation. Now we've removed all reference to x and y from here, and it's quite a nice expression in terms of r and theta. Okay, still more or less the same kind of structure. Sum of the squares in derivatives with x and y, still the sum of the squares for derivatives with r and theta, and you've got this extra parameter 1 over r squared multiplying the derivative df d theta. Okay, but our main tool, of course, was using the chain rule equations up there. Okay, so that's the kind of thing we were looking for. Is that okay? Any questions about that? Oh, sorry. Oh my God. Yeah. Yes. Come from or gone? This. We go to the next line. Well, you see, what is this numerator? What is x squared? No, it's the square of r. Remember, r is the square root of the sum of the squares. Yeah? R is the square root of the sum of the squares. So this is r squared. Yeah. Is that okay? Any other? Okay, so the chain rule equations can do that. They can take some kind of expression involving derivatives with regard to one coordinate system, and maybe if it all works out okay, you can push it across and get the same quantity, it's the same thing, but expressed with reference to a different coordinate system. Question 2 there is quite a different thing. We'll have a go at that now. So a right circular cone. What's a right circular cone? Well, probably just goes by the name of a cone. It's a cone. It's got a circular base, and the apex is above the center of the circle. So that's our cone. So what kind of cone is it? It's got height 15 and radius 10. So this is 10 centimeters on the radius and 15 on the vertical, on the height. But it's some kind of a dynamic cone, and the radius and height are changing as described in the question. So let's start to give these names. So r equals radius, h equals the height, It's very late on a Monday. Height. Okay, my language break. There's no h in the end. It's crazy. Jeez. Losing my mind. Okay, height. My Irish accent coming through. Right, so what's going on? So these things are changing. So R and H aren't fixed quantities. R and H are they're functions of the time variable t. So how should we describe them? We should be able to get explicit descriptions of them. Well, the radius is initial value 10, and the height is initial value 15, and we'll take time 0 being the starting point, and then let time go on from that. So so what's the height doing? The height is increasing at a rate of 0.2 centimeters. So the height is 15 plus t over 5, fifth of t. And is the radius, what's the radius doing? The radius is decreasing at a rate of 0.3 centimeters. So that's doing minus 3 over 10 t. Yeah. Does that seem sensible? And we want to know what's happening to the volume at time 0 at this moment. Is the volume increasing or decreasing? It's not obvious. It doesn't leap off the page at you because the radius is decreasing, so that will decrease the volume, but at the same time it's getting taller. So that will want to increase the volume. So what's the combined effect? So we need the equation for volume. So the volume is given by, well, it's based on the area of the base, but pushing that up through the cone, you get a third times the height times the area of the base. So a third pi r squared h. Now that's v expressed as a function of two variables, r and h. Yeah, it's a function of two variables. But really, since r and h are now, we know, are just functions of a single variable, t, really there's a function v of t floating around somewhere. And we want the derivative dv dt, okay? So we require the derivative dv dt, which comes from the chain rule equation. So dv dt is going to be dv dr by dr dt plus dv dh by dh dt. Easy peasy. Okay, there's only one chain rule equation here because there's only one new variable. We've got the single new variable t, which is parameterizing both the radius and height. So we just start plugging these in. We know what v is as a function of r and h. We know what r and h are as functions of t, so we can put down all these partial derivatives. dv dr is going to be 2/3 pi r h. dr dt is minus 3/10. dv dh is 1/3 pi r squared. And dh dt is 1/5. So this is the rate of change. That's the rate of change of the volume at any particular time. So at time t equals 0, the volume is changing with a rate, well, it's going to be dv dt evaluated at t equals 0. So we want to take this expression here and evaluate it at t equals 0. So what do we get? We get 2/3 pi. Now the radius at time 0 is 10. The height is 15. And you've got a -3/10. And then you've got a third pi. The radius is 10, so that's 100 by a fifth. Apparently that comes to -70/3 times pi. Easy to see. Well, you get 20/3 pi from the second bit, and you get 45, 90/3 pi from the first. -90/3 pi from the first one. So -90 plus 20 gives you a -70. Well, what can you say about -70 pi/3? Well, point is it's negative. So the volume is actually decreasing. So the shrinking in the radius is enough to overcome the stretching in the height to actually pull the volume down. Okay? So the volume, just a conclusion, we could say the volume is decreasing at the rate -70/3 pi, so it's approximately -70 cubic centimeters. What's going on here? Things are happening every minute. So so approximately -70 cubic centimeters per minute. Is that okay? I mean, alternatively, we might have just taken our expressions for R of t and H of t and just substituted them in straight away, and we would have got out a big long formula for the volume in terms of t. So we would have had explicitly the volume as a function of the single variable t, and then obtained dv dt. But the chain rule gives you a more kind of structural view of the derivative dv dt. It allows you to see it as a mixture of dv dr and dv dh multiplied by how fast r and h are changing respectively. Yeah. Sorry, yeah. Very well spotted. So it's changing at the rate of -70 over whatever. But of course, if you say it's decreasing, then you don't include because that suggests it's increasing if you say it's decreasing by a negative amount. Thank you. Okay, maybe let's jump to question 4. Question 3 is quite similar. Maybe we'll come back to that. But I'd like to, if I could, show you the spherical coordinate system and talk a little bit about that. So question 4, so we've got a parametrized motion of a particle in the plane. And its x-coordinate is changing linearly with respect to time, but the y-coordinate is changing in a quadratic fashion with respect to time. So the motion of the particle is parametrized by t. As x of t is 2 plus 3t, and y of t is t squared plus 4. Now, what's the question? What's the question? At what rate is the distance of the particle from the origin changing at time t equals 1? So the particle starts at position 2, 4, t equals 0. And after 1 second, after 1 second, it gets to position 5, 5, 5. Okay, but when it's at that position, How quickly, at what rate is it getting further from the origin? That's the question. What rate is the distance of the particle from the origin changing at time t equals 1? So to answer the question, we need to evaluate dr dt at t equals 1. Where r is the radius. Or radial distance of the point from the origin. So we can go to one of the chain rule equations. I mean, again, you don't have to go via the chain rule. You could now, since you know x of t and y of t, and you know what r is in terms of x, it's the square root of the sum of the squares. So you could just produce an expression for r solely in terms of t. But it might be quite complicated because it's going to be the square root of a quartic in t. Because y is quadratic in t, so when you get y squared, you're going to have t to the power 4, and you'll have all sorts of other stuff. So it'll be the square root of a power 4 polynomial. So it mightn't be the cleanest thing to handle directly. So why not go through the chain rule? Since we've already, in the earlier question, we've already had the derivatives. Well, we already know the connection of r to the radius. Yes, from the previous question. Okay, so the chain rule equation is so this gives dr dt as a mixture coming from dr dx, dr dy, and we're multiplying by dx dt and dy dt, and you're adding them together. And dr dx, dr dy we have from the earlier question. Don't we? Dr dx is x over r. And dr dy is y over r. Dx dt is coming from here. That's simply 3. And dy dt is coming from here, and that's 2t. That's an r there. So we can say we've got this quantity here, 1 over r times 3x plus 2ty. Now, okay, this isn't fully translated into any particular coordinate system. It's a mixture, in fact, of all three. You've got the time quantity in there, the x and y coordinates, and now also the radial, the radius coordinate r. So it's a bit of a, it's not a particularly beautiful expression or anything. It's quite a mixture of different things, but it's probably going to be quite easy for us to calculate with, given what we have here. So we need to evaluate this at t equals 1. So at t equals 1, we have, well, x is 5 and y is 5. And so r is, well, what's r? R is the square root of, sorry, 25 plus 25, square root of 50. But 50 is 25 by 2, so it's 5 by root 2. 5 by root 2. So now we've got values for r, x, and y, all at t equals 1, so they can go into the expression for dr dt. So dr dt at t equals 1 is going to be 1 over 5 root 2 into 15 plus 10. This gives us 25 over 5 root 2. Gives us 5 over root 2. 5 over root 2. Now, first thing maybe to note about that is it's a positive quantity. So our point is getting further away from the origin at t equals 1. It's not moving back closer to the origin. It's actually on its way out, on its way away from the origin. So we could just put that into the conclusion. So particle is moving away from the origin. It's getting further from the origin at the rate 5 over root 2, whatever the units are, what the units are. Centimeters per second, yeah. So that's the rate of change of the radial distance. It's increasing at the rate of 5 over root 2 centimeters per second. And again, coming from, we made good use of our chain rule equation to get us to that. And it's just, we just did some efficient work with, now there was a bit of a hoo-ha to get dr dx and dr dy, but we've done that already, so we could call upon those known values of x over r and y over r. So we ended up probably evaluating that a lot cleaner than if we had just formed the explicit equation for r in terms of t. Okay. Any questions about that? Or? Yes. If it's the radius, if r is the radius, yeah. And if you forget it, is it x? If you don't quite remember it, you just have to go back and derive it. So r is the square root of the x squared plus y squared. So you can differentiate that with respect to x, and you'll see it again that it's x over r. Yeah. Okay. So the last thing to show you is just everybody's pretty familiar with the polar coordinates, but maybe a bit less so with the spherical coordinates, which are in 3 dimensions. I have asked questions based on these in previous year's coursework and exams and so on. They're quite a useful device. So for describing, well, not circular, spherical stuff, spherical matters in 3 dimensions, we can use spherical coordinates. I think some people call them spherical polar coordinates maybe, but let's call our things spherical coordinates. So r, theta, and phi. So it's not surprising it takes three of them because you're in a three-dimensional world. So it's pretty much going to need three pieces of information to pin down any location in 3 dimensions. And what they mean, well, we have our usual Cartesian coordinates x, y, and z. So think of x, y being the ground plane. X is kind of coming out a bit towards you. Y is going back into the page. So here's our point somewhere hovering up here. Here's a point P. So what are these things, r, theta, and phi? Well, r is again the radial distance. Where will I put that? Let's stick up here. So you got the radial distance r. That's quite nice. No, I mean, for instance, spherical coordinates are used a lot in astronomy. Say, if you think about if you're in observational astronomy, when you're trying to work out where to point your telescope in the sky, it doesn't make sense to give x, y, and z coordinates of a star relative to the Earth, because that's not really what you need to know in terms of where to point your telescope. To point your telescope, you need to know, well, which direction should you face, and that's one angle. So which direction should you face in? The other angle you need to know is how high to point your telescope, whether it's down low near the horizon or it's straight up that way. So there's a second angle there. And then lastly, maybe r, the distance of the object from the Earth. Okay, you don't know that to point your telescope at it, but that's the third piece of information that would pinpoint that location in space. So r is the radial distance. We drop a perpendicular from the point down onto the plane. So that's a perpendicular projection of the point P down onto the plane. And that gives us a projected radius. So you've got the actual radius line from the point to the origin. But when you project it down to the xy plane, you've then got the projected radius. And theta is this angle here, which the projected radius makes with the positive direction of the x-axis. And then lastly, the angle phi is the angle that the radius itself, the radial line itself, makes with the positive direction of the z-axis. Okay, so r is the radial distance. Radial distance to a point P. Theta is the angle between the projection of r to the xy plane. So that's this dotted line here and the x-axis. And phi is the angle between the radius and the z-axis. Positive direction of the x-axis, positive direction of the z-axis in both cases. Now, these angles have names. Theta is, now they're azimuth and zenith. I think zenith is the phi. Yeah, phi is the zenith angle. And this is the azimuth angle. So what we'll first want to describe is, okay, well, that's how they look in the diagram as related to x, y, and z, but what are actually the precise expressions that give you x, y, and z in terms of r, theta, phi? So that's one question. And it's probably going to involve cosines and sines, because there are a number of triangles suggested in that picture. But first, be careful, just a note of warning. Different subjects or different disciplines This is something that one of the many things humankind hasn't sorted out yet. So different disciplines, so maths, engineering, physics, haven't agreed on conventions for theta and phi. So some books will call this angle phi and this one theta. Chaos. It's like, you know. Generally in mathematics, these are the names used. But if you go to engineering or physics, they might have swapped those names around. So just, if you're looking at different books, just be aware that that can happen. And go back to where they've defined these things and just make sure you know how they've set it up, okay? But the linking equations, what are the linking equations for these? Well, Z is probably the easiest one to write down, first of all. See, with Z, you've got some kind of a right-angled triangle there. Sorry, what am I talking about? Putting it up here. We're talking about locating this point P. So R is the hypotenuse of that triangle. Phi is one of the angles. So Z is going to be R times the cosine of phi. That's the adjacent side to phi. The opposite side to phi is actually the same as the projected radius. The length of the opposite side to phi is actually the same as the projected radius. The projected radius has length R sine phi. And this feeds into equations for x and y. So this projected radius here is actually R sine phi. But that is the hypotenuse of this angle here. And that angle here has its adjacent and opposite sides to be x and y respectively. So this R sine phi term acts as the hypotenuse down here. So it plays the role that R played in the two-dimensional polar coordinates. Okay, so x is going to be R sine phi cosine of theta, and y is going to be R sine phi sine of theta. Okay, so those are the linking equations. And we're going to make, one of the places we're going to make use of these spherical coordinates is in tackling three-dimensional integrals. Integrals over volumes. So where you're summing up the behavior, or you're accumulating the behavior of some kind of scalar function defined in space. So when you're integrating over volumes, you may wish to change to polar coordinates, because the volume you're integrating over may be spherical or half spherical or something. So spherical polar coordinates might be the thing to use. So we can set ourselves the problem of evaluate or find an expression for the Jacobian determinant dxyz dr theta phi. So to get a formula for this in terms of r theta phi. So it's some kind of formula that might have an r in it, might have a theta in it, might have a phi in it, but what kind of expression can you find for this this Jacobian? Okay, so that's something we can tackle in the tutorials, or I'll discuss in the lecture next week. Okay, so we'll end it there.